Hello everyone. My name is Hello everyone. My name is Xuefeng William Wang. I'm presenting this paper when your fitness tracker betrays you, quantifying the predictability of biometric features across contexts. This paper is published at 2018 IEEE Symposium on Security and Privacy by Simon Ebers, Giulio Lovisotto, Andrea Patini, Marta Kwiatkowska, Ivan Martinovic from Department of Computer Science at University of Oxford, and Vincent Landers from Amalfi, Switzerland. So there are common biometric authentications which have been widely used, like fingerprints and face recognition. Yeah, we use those probably every day on the smartphone authentication. But those biometric authentication can be easily attacked. For example, the fingerprint. The attacker could get the victim's fingerprint from lifting off on a smooth surface like a coffee mug. The face recognition for the face, normally the victim's face picture could be available in social media. It's in two-dimensional. So there are more biometric authentication has been considered, and the behavior biometrics has been becoming a popular research subject. Behavior biometrics is more like mouse check, your mouse movement, the gait, the way you walk, or ECG. So those behavior biometric could uniquely identify you. The authentication mechanism, biometric authentication mechanism, normally consists of two steps. First, the biometric information has to be collected. And the second, that biometric information will be presented to the authentication system. So this paper is more focused on how to attack the victim's biometric information, the first step, the information collection, rather than presented to the authentication system. The key challenge here is the biometric features depend on not only the user, but also on the context of the measurement. The context really mean like for example, for the gait, how you walk, the context may be like the sensor of collect those how you walk, like a smartwatch or a smartphone, and the location of those sensor is placed on user, like either on the arm or on the chest or on the wrist. So the feature distribution, the values will be different on different if they are collected from a different context. So here, that's the biggest challenge. So the cross-context biometric features. So the researchers are trying to answer this question. Are the context-specific changes in features systematic and predictable? Meaning, if a feature is collected from one context, is that can you predict this the same feature but in a different context? For example, the gait. If the attacker got this victim's gait distribution from one source like a smartwatch, but can he predict systematically the feature values in the target context? Maybe that's like a smartphone and placed on the arm. So the researchers formalized an approach to automatically derive a cross-contact feature mapping based on population data. The population data is some data attacker can easily get, like maybe public available, or he can use some way to easily collect those. So they use this method, this mapping, use this methodology to assess and compare the security of 5 biometrics: gait, touchscreen dynamics, ECG eye movement, and mouse movements. They conducted a study with 30 participants for all biometrics in different contexts across 2 separated sessions. So there are related attacks research from the research papers. There are imitation attacks for those biometric authentication. Most those attacks like imitation attacks. There are basically 2 categories. One is manual imitation. Another one is robotic imitation. So the biometric authentication, they have attacked like the touchscreen input pattern. For example, like a touchscreen input pattern, the attacker may like over the shoulder watch how the victim use the touch screen, the usage pattern, how they swipe, they try to, then attacker can try to manually imitate that user, try to impersonate it. Or like, or the attacker could trick user to visit some website, for example, for the mouse movement, how the mouse, like the user accelerate the mouse and how to click, the duration, like those. And the attacker could trick the user to a malicious website, and that website can record how user's mouse movement, the movement pattern, then they can try to manually imitate it. Or there are, this picture shows a research paper. The researcher developed used this Lego mindstorm to do an automatic imitation of the user's touch screen input patterns. So they collected the touch screen input pattern from population data. Then they try to imitate that using this robotic imitation. So the threat model we are concerned here is the adversary attempt to bypass a biometric authentication system, like a login system, right? A smartphone login system, using incomplete biometric information about the victim from another context and combining it with the population data. Yeah, let's look at this picture. It's explain what the threat model is. So here we have the victim, and victim uses this smartphone, and this smartphone is authenticated with the victim's like a biometric information, and that biometric information is very securely stored in the smartphone. So the biometric information, right, is depend on the context. So let's say this, for example, for the gait. So assume this smartphone is using this victim's the gait to authenticate him. The smartphone has an accelerometer, so it can record those how user walk, the acceleration, like those. And assume this smartphone is placed on user's arm to collect those data. And so that defines the target context, like smartphone on the arm, and the user is like walking. So that data is used as the target biometric feature. So that is assume that is very secure, because most time the smartphone right now is can very securely storing those biometric template for the user. Like for example, like Apple Touch ID, they use this secure enclave to store users like a fingerprint or some those face recognition, those very sensitive data. So those are considered very secure. So the attacker has no way to steal those target data, the feature in the target context data. But at the same time, this victim actually carries a smartwatch, which also has an accelerometer, so it also records user's gait, that biometric information. And the smartwatch, comparing to the smartphone, is much less secure. One reason probably is the smartwatch is not really for authentication. It's just to record like how the activities. So assume the adversary have a way to obtain that insecure data. But the smartwatch, the data smartwatch collected for the gate is for a different context than the target context. It's like a smartwatch is on the wrist, and maybe attacker obtained that data when user is like running. So it's basically the source context is different than the target context for the victim. So adversary has the source victim's source feature data. Then he asks a population. He get the data, ask the population, maybe a bunch of friends to carry on the smartwatch and the smartphone for both source and the target context. And he asked those friends, give him those data. So he has a way to collect the gate feature data from both source and target context, but for the population data, not the victim data. So here he has those data. He has incomplete victims data, only the source, but he has the population data, which has both source and the target context. So the attacker is trying to use all of those data to impersonate the target context feature information. So that's the threat model. So the researchers designed an experiment. They hired like 30 participants, and the experiment was carried on two separate but identical sessions, which are 5 days to 30 days apart. Each session, the participant has to go through a series of tasks. Like at first, they have to, the researcher trying to collect the mouse movement pattern. So they ask the participant to click on a grid of right angles, and one of the right angle has the picture, and the user has to click on the picture. Then the picture move to another right angle. So they try to record the user's click pattern. And for example, for the eye movement, they have a little infrared to shine a light on user's eye and collect the reflection of the cornea. For the touch dynamic, they have designed a little spot difference, a little game. So user has to swipe to see the difference between two pictures. So basically, they designed a series of tasks the user has to go through. Each time, for each task, they equipped with different, they try to make it many different contexts. For example, like ECG, they may have very different sensors, like a mobile and medical devices, and they have some more advanced authenticator device, and user perform those tasks, the ECG tasks on like rest or running or like walking, different. So they make a different context. Then they use some common state-of-art practice to extract those feature information from the data. Yeah, those are some each feature extraction algorithm. They have a cited paper for kind of proven methodology. Then it comes the main part of the mapping methodology. So this the researcher is trying to develop this mapping. That's the goal of develop this mapping across the context. So this idea is generalized from the paper, from the same first author, Simon Ebers, Broken-Hearted, How to Attack ECG Biometrics. So basically, they generalized from that idea. So given a context and a feature, they associate each user a random variable. And the cross-context mapping transform each source context random variable to maximize statistical similarity to its corresponding target context random variable. The final output of the estimation for a pair of source target contexts is a set of functions, one per each feature, that maps the values of features measured in source to the target. Yeah, this can be more explained in the following equation. So here's the cross-context mapping estimation equation they have. So their goal is to try to find this function, which transform the source random variable to generate output. But that output, they will try to find that output to be very similar to the target random variable. So in this equation, we can see in the big sigma there is the statistical distance, the lowercase d function. That's the statistical distance between the two distribution. The one distribution is look at the right side. That distribution is for the XUIT. That is the random variable for the user for the specific feature in the target. T means the target context. Then they get this called a cumulative density function. It's a distribution of the random variable. And so that's one value. Then that's the target distribution. And they have the source XUIS. That's the source random variable. And so the f theta, that's the function they are trying to find. So they apply this transformation function to the random variable for the user for that specific feature in the source context. Then they get another cumulative density function. So those two cumulative distribution has a statistical distance. They will sum it up, then divide by n to get the average. So the goal is to find the function which minimize the distance. So you try to find the function which makes those two distributions as close as possible. So that's the mapping estimation, and they did a little further refinement to find the outlier using some outlier detection algorithm and remove the outlier. Then they defined a notion of unpredictability score. So for feature G, they computed the optimal cross-context mapping and the prediction error for the victim source observation to the victim target observations. This is defined as the unpredictability error. So this is pretty much is like how different the transformed distribution comparing to the target distribution. The bigger the difference, it's more unpredictable. So they designed this value to be between 0 and 1. So smaller means more predictable, bigger means is less predictable. But different feature may have a different contribution to the final biometric recognition. So they introduce this relative mutual information weighted score. So the more distinctive feature will have a higher weight. So in the end, they calculate this weighted unpredictability score for the whole biometric. The main advantage actually of this score is not its absolute value or scale. It's rather is actually the comparative capability. So this score can help the designer to compare to find which feature, which biometric is more secure or more vulnerable. The more unpredictable is more secure. They have their evaluation methodology involves like the cross validation. They use they call leave one out cross validation. Basically, for the 30 participants, they pick one as a victim, and the rest are the population data. And they consider different scenarios. For example, like whether the attack happens in the same session or across different sessions. And they also consider like the average value, the minimum value, and all the values. Oh yeah, so basically they have they assume attacker has that scenario attacker has obtained one individual source feature distribution, or attacker has obtained all sources, a full set of the source feature values. So those are different scenarios they considered. Then it comes to the results they got. They presented the result in a table. So in this table is the numbers of unpredictability scores, and you can see there are 5 different biometric ECG, eye movement, etc. And there are different scenarios, like a same session or across sessions. And in each biometric, they have different contexts. So the first one is the target context, and the value is the aggregated and mean and all. So for the population data, they have many different contexts. For example, ECG, they have a fitness tracker at rest, or mobile at rest, or fitness tracker when walking. So they calculate all the unpredictability scores for those different population contexts. The average and the mean and all means average is just the aggregated average value. The mean means so the attacker only obtained one source. The all means attacker has all the sources values. So from those numbers we can see easily we can see the gate and the ECG has the most unpredictable biometrics. So they tend to be more secure. And we can also see the gate is almost double of like a mouse movement. We can also see like from the same comparing to look at the same session or cross sessions. The cross session has more higher unpredictabilities, which means the implication is if attacker can get the most recent data, meaning it's kind of like in the same session, it has a better chance. Also, look at the average, mean, and all values. So if the attacker pick a good source, appropriate source, which is the mean, then it may have a maybe 10% better chance to imitate the user. From the mean to all, which makes sense. If an attacker has a large number of input sources, feature values, it will have a better chance to get this right, to get the better imitation. So they also dive into each individual feature analysis. for example, this touch dynamic, the unpredictability score for this, they listed the different features like a stroke, pressure, stroke area. So this is for the touch dynamic, and the target is a middle-end phone. The population is low-end and high-end phones. We can see stroke duration, for example, is very predictable. The unpredictability score is very low. So this could help the system designer when they look at this, when they pick the features in the feature set, they may say, oh, this stroke duration is very predictable across context. So maybe at least it should have a lower weight, or maybe just not included this feature in the feature set. So they have more details actually for a few other feature analysis in the paper. Also, they look at the population, whether the population they picked matters or not. So based on these two diagrams, we can see at the beginning, it does the unpredictability score drop a lot when the population is very small, like less than 5. But beyond the 10, the unpredictability score actually become very stable. So which means the 30 participants the researcher has used is good enough to predict this. So here we come to the conclusion. So the researcher develop an analytic framework that measures the predictability of biometric features across different contexts. Yeah, this is quite useful for the system designer also to make sure, yeah, the different they realize the attacker could predict the feature distribution from a different source. So they have to consider that when they design the authentication system. The unpredictability score, which can be calculated for both the individual feature and the complete biometrics, which is useful for the designer of those authentication systems. They can, for example, like a gate and the ECG, right, tends to be the better biometric, which has a higher unpredictability score. So means more secure than touch dynamic and the mouse and eye movements. So yeah, they basically they found this transformation function which can transform from across the context to predict the feature, the biometric information from the source to the target. So this concludes this paper presentation. Yeah, thank you.